Greetings. This video is for Calc 2 and volumes by revolution, or revolutions of solids it's sometimes called. And this really shows up in chapter 6.2 and 6.3 in our textbook. So for this video, I want to talk specifically about the disk method, and the other video I talk specifically about the shell method. Okay, so the disk method, sometimes we call the washer method, disk method, washer method, depending what book you use, has a general form. So the area is equal to the integral from a to b, and then we have a pi, and the pi gets multiplied by the quantity of the outer radius squared minus the inner radius squared. Now sometimes you'll see this written in a textbook a little bit differently. Sometimes you'll see it written in the textbook as the area equals the integral from a to b of pi times outer radius squared minus pi times inner radius. And that's really just the same thing, and squared. The only difference between those two things is I have factored out the pi's in each term and written them out front, and then just have the outer radius squared minus the inner radius squared. And then we have a d delta, right? So this sort of change in either x or y. And I've written it generically because we don't know whether it's going to be with respect to x or whether it's going to be with respect to y. We have to see the context of the problem to figure that out. So remember one thing that's really important, and if we can kind of get a grasp on this, I think it can really help us. The outer radius and the inner radius are distances from the line of rotation to the function. So the radius is the distance from the line of rotation to the function. That's always true, no matter what method we're using. So when we're talking about a radius, it's from the function to the line of rotation, or from the line of rotation to the function. So if I call the line of rotation capital L, and I talk about the function as being lowercase f, we don't have to worry about whether we do L minus f or if we do f minus L, because we're going to square it anyways, right? So we're doing f minus L and squaring it. And we're doing, or if we do L minus f and squared, it doesn't matter, because L minus f when we square it is exactly the same thing as f minus L when we square it. Those are equivalent things. Now the reason I point that out is because there are a lot of tutors, a lot of professors, and a lot of books, frankly, who make a huge deal out of whether or not you should use L minus f or you should use f minus L. Doesn't matter when you're using the disk method, because you're going to square them, and that's a distance, right? Just think about it. The distance from your house to the nearest mire is the same whether you're going from your house to mire or whether you're going from mire to your house. The distance is exactly the same. Those things are equal. So how we write them doesn't matter. If we're squaring it, we're taking the absolute value effectively when we square it. Okay, so f minus L or L minus f doesn't matter. Just think of it as the distance from the function to the line you're rotating it, and then we're going to square it. Or it's the distance from the line to the function, and then we're going to square it. Okay, so here's something that you can remember. It'll help you solve these problems very easily. If we're going to use the disk method for disk, if L equals the line of rotation and L is about the x equals a number, then we use dy. If L is about y equals a number, then we use dx. So the disk method, dy versus dx, is always the opposite of the line of rotation. So if we're going around y equals 2, so let's say we were doing y equals 2. If we were about y equals 2, then we're going to use dx. If we were going around x equals minus 5, then we're going to use dy. It's always the opposite, right? always the opposite. If it's around x equals a number, we use dy. If it's around y equals a number, then we use dx. It's important to remember that the x-axis is the same as y equals 0. And the y-axis is the same as x is equal to 0. Don't let that trip you up. So if I am rotating about the x-axis, on your paper, if you have to, cross off the x-axis and write y equals 0. Because y equals 0 is the same as the x-axis. So I'm using y equals a number, then I use dx. If I was rotating about the y-axis, that's x equals 0, and I would use dy. So that's one thing that can get you in trouble if you're not careful to remember that. So x-axis is y equals 0. Y equals 0 means we're going to use dx. Y-axis is x is equal to 0. X is equal to 0 means we're going to use dy. With the disk method, it's always opposite of the line of rotation. Okay, so let's do an example. I have a region enclosed by the curves y equals x and y equals x squared, and we're rotating it about y equals 2. So the first thing we always do is draw a picture. Draw a picture, draw a picture, draw a picture. So I draw a picture, this is x and this is y. This is y equals x. It's not a perfect picture. I missed a little bit down here. It was a little off, but close enough. Y equals x. And then y equals x squared. Y equals x squared looks something like this. And then we're rotating about y equals 2. So I also sometimes have to remember when I'm sketching that where I draw my rotation about, make sure I don't put it in the wrong spot. It would be a mistake to draw it down here and say this is y equals 2. That would be a mistake, right? Because it's below the bound. That's my bound. So sometimes I have to kind of get a sense of where is my bounds going to be first, and then I can figure out where my line is. But I'm familiar enough with y equals x and y equals x squared to know that this is going to be above that. So this is y equals 2. And then most people draw a little arrow to remind us it's going to rotate. So that's the first thing I did. I drew a picture. The second thing I'm going to do is figure out my bounds. And I want to point out that sometimes in the problem they tell us our bounds. But in this case, the two curves close each other off, so I have to figure out the bounds. And remember what we're figuring out. We're figuring out what is this point here where the two meet, and what is this point there when the two meet. So I need to figure out this point and that point. That'll be my bounds of the problem, unless they tell us something different. Okay, so how do we do that? Well, that's easy enough. I set the two equal to each other. So I want y equals y, right? That's what I want. Well, one y is equal to x, the other y is equal to x squared. So I just solve for that value. So I get x minus x squared equals 0. And I factor out an x and I get 1 minus x equals 0. And that tells me that x is equal to 0 or x is equal to 1. Okay? So I can label that. When x is equal to 0, what's y? Well, when x is equal to 0, y is equal to 0. So that's my one point is 0, 0. And my other one, when x is equal to 1, what's y equal to? Well, y is equal also to 1. Okay, when I put them both into the functions, that's what I get. So I figured out my bounds. Number 3 I need to do is figure out if we're going to use the disk or the shell method. This is always a question we have to figure out. Which of the two methods am I going to use? Now obviously this video is about the disk method, so we're going to use the disk method. In practice, we don't always know, right? But sometimes we do know. How do we know? Well, that's because sometimes it says, using the disk method find. Or I'm looking at my homework set and I go, oh, this is in section 6.2 and that's the disk method. But I don't always know, right? So how do I figure out if I'm using the disk or the shell method? So what I do is I write, we are going about y equals 2. Okay? So if I use the disk, I would be doing dx. I'm going to do the opposite with a disk. So the question I need to ask, can I find an integral with x stuff and then dx, right? So in other words, can I put in an integral with f of x? The function inside has x stuff. Is that easy to do? Because I need dx on the outside. And then on top of that, can I find a and b with my x stuff? So in other words, is my bounds of integration easy to find in terms of x? If the answer is yes, then use a disk. If the answer is no, then use shell. Okay? So it's easy to find the x stuff in this case. I've got them written down already, right? So this is x stuff. This other one is y equals x squared. X stuff is easy to find. My bounds of integration in terms of x are easy to find. 0 to 1, okay? And I'm going to rotate around dx, so no worries. Okay, so then I use find the outer radius and a radius and the inner radius. By the way, you can do it the other way around, but I always do the function minus the line. I always do f minus l. You can do l minus f if you want, that's fine. The only reason I do f minus l is looking at the picture, I can easily see which function is outside. So I know that this is my line of rotation. And if I did it the other way around, if I did it L minus F, which again, it doesn't matter. If I did L minus F, maybe I make a mistake and I'm starting here and I'm drawing down and I hit this one, I go, oh, that's my outside, which would be wrong, right? When I do F minus L, I look at my picture and I go, which of these two is furthest away from my L, my line of rotation? Well, it's this one, right? This is the furthest one away. So that's the outer radius. So I do that one, that f minus L. So x squared minus 2. So x squared minus 2. Don't forget to square it. So that's my outer. And then what's my inner? Well, here's my inside one. Here's my line. And this one is x. So then x minus 2. So my inside is x minus 2. And that's my in radius. Okay, all I have to do is set up the integral and solve. So the general form says from a to b, and pi, and then a radius out squared minus a radius in squared, and then d theta, or d delta. And in this particular case, we're going to do with respect to x, and we already have everything written out that we need. So this is pi. My outer radius is x squared minus 2, and square it, minus my inner radius was x minus 2. I forgot to square it up there, and square it. And then I have dx. I check to make sure, does everything inside my function have x's in it? It does. Dx. And now I just have to find my bounds of integration. But that's easy enough. I go from 0 to 1. So I set up that 0 to 1, and then I just evaluate that integral. And when I evaluated that integral, I got pi times 8 over 15. Okay, so hopefully this video will help you. The biggest key to, I think, to get from this is it doesn't matter if we do f minus L or we do L minus F, because we're going to square it. Again, I always do the function first, so it's easier for me to find what the outside is and the inside is. So I do f minus L, then I square it. And then also, I think the second biggest thing to take away from this is you have L about x equals a number, then we use dy. And if we do L about y equals a number, we use dx. And remember, the x-axis is really y equals 0. So then you would use dx. And the y-axis is really x is equal to 0. So then you would use dy.